On the 1st of May, 1851, Queen Victoria stepped into a building that had no business standing. It stretched 851 feet through Hyde Park, a third of a mile of glass, and climbed 108 feet into the London sky. Inside, full-grown elm trees stood untouched, their branches spreading beneath a transparent roof. Fountains ran between them. Around them, more than 100,000 objects waited on display. Locomotives, diamonds, power looms, a folding piano, stuffed elephants. 6 million people would pass through before the year was out. Nothing like it had ever existed. Cathedrals took a century to raise. This had gone up in months. It carried roughly 900,000 square feet of glass, nearly a third of Britain's yearly output, hung on a skeleton of iron so slender that visitors swore the walls were made of nothing but light. Rain drummed on the ridged roof and vanished into hidden channels. Sparrows got trapped inside, and the story went that the Duke of Wellington solved it with a single word: sparrowhawks. Contemporaries reached for a name and failed. The satirical magazine Punch supplied one almost by accident, the Crystal Palace, and it stuck. But the name flattered the mystery instead of explaining it. How do you build a glass hall the length of 5 football pitches, tall enough to swallow living trees, and finish it in time for a fixed opening day announced to the world? Because that was the trap. The Great Exhibition had a date, nations had been invited, exhibits were already crossing oceans. There was no option to run late, no century to spare, no margin at all, and the material that would later make such spans routine. Structural steel, the stuff of every skyscraper that followed, did not yet exist, not in any usable form. The engineers who raised this palace worked with older, more temperamental metals, and with a deadline that should have been impossible. To understand how they did it, you first have to understand what they did not have. In 1851, the age of steel had not yet begun. Steel, in 1851, was a jeweler's material. It existed in sword blades, in watch springs, in fine cutlery, but only in small, costly batches, melted in crucibles, a few pounds at a time. To build with it, to pour it into beams by the 1,000-ton, was economically unthinkable. Henry Bessemer would not blow air through molten iron and stumble onto cheap bulk steel until 1856, 5 years after the palace opened, and even then it would take a decade more before engineers trusted it. The men of 1851 had to build a future out of the past. What they had was iron and 2 tempers, each with a fatal flaw. Cast iron, poured molten into molds, was cheap, fast, and enormously strong when squeezed. A cast iron column could carry a mountain pressing straight down on it. But pull it, bend it, or shock it, and it snapped like glass, with no warning and no give. It was brittle. It failed suddenly. Wrought iron was the opposite. Hammered and rolled to drive out the carbon, it was tough and springy. You could stretch it, bolt it, bend it, and it would yield before it broke. But it was labor-intensive and costly, and under a steady crushing load, it could sag and creep. Neither metal alone could raise a building. Stone, the third option, was heavy, slow, and hopeless for spanning wide, open, light-filled space. So the engineers played the metals against their weaknesses. Cast iron went where the loads pushed, the vertical columns, holding the weight straight down. Wrought iron went where the loads pulled, the horizontal ties, and the lower edges of the girders, taking the tension. Each metal did only what it was good at, and nothing it was bad at. It was a language of hard compromise, learned in railway bridges and factory floors, some of which had already buckled and killed. That was the toolkit: 2 flawed irons, sheet glass, and a ticking clock. And it would take an outsider, a man who had never trained as an architect, to see how to assemble them. Joseph Paxton had never designed a building for people. He was a gardener, the head gardener at Chatsworth, the Duke of Devonshire's estate in Derbyshire, where he had risen from a laborer's son to the most trusted man on the grounds. And Gardner, as it turned out, had been quietly solving the glass problem for decades. to grow pineapples and exotics through an English winter. They built greenhouses, and Paxton built the most ambitious in the world. At Chatsworth, he raised the Great Conservatory, a glass house 277 feet long under which carriages could drive. To glaze it efficiently, he perfected a system he called ridge and furrow. Instead of laying glass flat, he set it in a zigzag of small peaks and valleys, angled to catch the low morning and evening sun and shed rain. He patented a wooden gutter, the Paxton gutter, a single grooved beam that carried rainwater on the outside and condensation on the inside, draining both at once. It was structure and plumbing in one repeated part. Then came the lily. In 1849, Chatsworth received a seedling of Victoria amazonica, the giant Amazon water lily, with leaves that grew 6 feet across. Paxton coaxed it to flower, the first in England, and stood his young daughter Annie on one of the floating pads to show it could bear her weight. He turned a leaf over and studied its underside, a radiating network of thick ribs and slender cross ribs, a natural framework in which thin members braced each other to carry a load far beyond their apparent strength. Nature, he said, was the engineer. Here was the idea that mattered. Not glass, not iron, but a principle. A large light structure could be built from many small, repeated members, each one modest, working together. Slim ribs, correctly arranged, could hold up a vast, thin surface. He had seen it in a leaf. He had already built it, in miniature, in a Derbyshire garden. What he had not yet done was draw it. And the moment that forced him came from a committee in London that was running out of options. The organizers of the Great Exhibition had a problem, and it was of their own making. A building committee, stocked with famous names, including the engineers Isambard Kingdom Brunel and Robert Stevenson, had invited designs for the Great Hall. They received 245 of them from across Britain and Europe and rejected every single one as too costly, too slow, or too permanent for a park that was meant to be handed back. So the committee designed its own. It was a brick monster, a low, sprawling mass of masonry crowned by an iron dome larger than St. Paul's, requiring an estimated 15 million bricks. It would take too long to build, be nearly impossible to remove, and the public loathed it on sight. With the opening date fixed and the clock running, the whole enterprise was drifting toward humiliation. Paxton heard of the crisis and asked for a chance. Then, at a railway board meeting in June 1850, distracted, doodling, he sketched his answer on a sheet of pink blotting paper. It survives to this day. In a few strokes, it laid out the entire concept. A tiered glass hall of repeated bays, a ridge and furrow roof, iron columns, the whole thing prefabricated and demountable. He worked the idea up into full drawings in 9 days. The genius was not only the look, it was the logic of time. A stone building must be raised in place, course by course, one slow trade waiting on another. Paxton's palace could be manufactured, its columns, girders, gutters, and glass cast and rolled in distant factories, delivered to the park, and bolted together like a colossal kit. Work could happen everywhere at once. That was the only way to beat the deadline, and everyone who understood construction knew it. He had roughly a year to opening. No conventional building could rise that fast. Only a repeatable, standardized system, the same part made thousands of times, stood any chance at all. Which raised the real question, the one the blotting paper didn't answer. How big should that one repeated part actually be? The answer began with a pane of glass. Paxton did not start from the building and work down. He started from the largest single sheet that British industry could reliably make and built the entire palace up from it. That sheet was 49 inches long, about 4 feet. The biggest pane Chance brothers could draw by their cylinder process at scale. Everything else would be a multiple of it. This is the reversal at the heart of the Crystal Palace. Most buildings are designed and then broken into parts. Paxton designed the part first and let it dictate the whole. The 49-inch pane set the spacing of the glazing bars. Those bars set an 8-foot bay. The 8-foot bays grouped into a master structural module of 24 feet. The distance between the great iron columns repeated again and again down the length and across the width of the hall. A single dimension propagated upward through the entire design, like a crystal growing from a seed. The payoff was total interchangeability. Because every bay was 24 feet, every column was identical, every girder identical, every gutter identical, every one of the hundreds of thousands of panes cut to the same size. There were no bespoke pieces, no one-off fittings to measure and trim on site. A girder from the far end of the building would bolt perfectly into a column at the near end. Parts arrived at Hyde Park sorted by type, not by location, because location no longer mattered. That is what made the speed possible. Interchangeable parts could be mass-produced in a factory, stockpiled, shipped in bulk, and installed by teams working in parallel without stopping to think. And it made the building flexible. Want it longer? Add modules. The famous transept, the great arched roof, raised to clear Hyde Park's living elm trees, was simply the module adapted, not redesigned. The grid absorbed even the trees. But a module is only a number until someone makes the glass. And to fill this one, a single firm in Smethwick would have to produce sheets on a scale no glassworks had ever attempted. A palace of glass needs glass, and in 1850, no factory on earth had ever been asked for this much. The order went to Chance Brothers of Smethwick near Birmingham, the only works in Britain capable of the job. They cast almost 300,000 sheets of cylinder glass, each one identical, 49 inches long, 10 inches wide, 16 ounces to the square foot. Laid end to end, the panes would have stretched for miles. Together, they amounted to roughly a third of Britain's entire annual glass output, swallowed by a single building in a matter of months. Cylinder glass was made by breath and muscle. A glassblower gathered molten metal on a blowpipe and swung it into a long cylinder, sometimes 5 feet tall. The ends were cut off, the tube slit down its length, then reheated until it slumped flat into a sheet. It was ancient, exhausting work, but Chance Brothers had industrialized it, running the process at a scale no one had attempted, feeding furnaces day and night. The genius was not the glass itself, it was the standardization. Because every pane was cut to Paxton's single master dimension, the 49-inch sheet that governed the whole grid, there were no special cases. No window was larger than another. No corner needed a bespoke shape. A pane made in Smethwick in December was interchangeable with a pane made in March and with the 10,000 around it. That uniformity turned glass into a commodity you could ship like coal. Panes were packed into crates, loaded onto railway wagons, hauled to Hyde Park, and sorted on site by size, because there was only one size. Not a single sheet had to be measured and cut to fit the building. The building had been designed to fit the sheet. Glass alone, though, is fragile and weightless. It could not hold itself up. To carry those 300,000 panes a third of a mile across the sky, Paxton needed an iron skeleton, and that skeleton had to be manufactured, tested, and raised faster than any building in history. The contract for the ironwork went to Fox, Henderson and Company of Smethwick, and they treated the Crystal Palace not as architecture, but as manufacturing. In their Birmingham works, foundries poured molten iron into molds around the clock, turning out the building's bones as a repeating catalog of parts. 300 cast iron columns, 224 girders, hundreds of miles of wooden glazing bars, all sized to Paxton's 24-foot module. Cast iron is strong in compression but treacherous, brittle, prone to hidden flaws that shatter without warning. So Fox, Henderson tested every casting before it left the works. Columns were loaded on a hydraulic press to prove they could bear far more than they ever would in the building. Girders were bent under measured weights to confirm they flexed and recovered. A part that failed was scrapped. A part that passed was numbered and shipped. Nothing untested reached Hyde Park. On site, the assembly ran like clockwork. More than 2,000 men worked the ground at once, and the sequence was choreographed. A gang of 8 could raise a column, drop a girder into place, and bolt the connection in minutes. Then, move down the line to the next bay. Every joint was the same joint. Every bay was the same bay. A worker who fitted one learned the whole building. The glazing was faster still. Paxton designed wheeled glazing wagons that ran along the roof gutters themselves, each carrying men and panes down the length of the nave. Sheltered under the wagon roofs, glaziers set the glass without scaffolding, and at their peak, 80 men fitted more than 18,000 panes in a single week. It was a production line laid horizontally across a London park. From the first column in September 1850 to a finished building, the palace rose in about 39 weeks. A structure a third of a mile long, enclosing 19 acres, assembled in the time a modern house might take. Speed on that scale had never been seen, and it could not have happened anywhere but here. But the real revelation was not how fast one palace went up. It was that the same kit could go up again, somewhere else entirely. When the Great Exhibition closed in October 1851, the Crystal Palace faced demolition. Instead, it did something no permanent building could. It was unbolted. Column by column, girder by girder, the entire structure was taken apart, loaded onto wagons, and carried 8 miles south to Sydenham Hill. There, between 1852 and 1854, it was rebuilt, not merely restored, but enlarged, with a higher barrel-vaulted roof and even more glass. The proof was total. A building that could be dismantled and reassembled, bigger, was not a building at all in the old sense. It was a kit. And kits can be copied. The idea leapt across borders almost immediately. New York raised its own Crystal Palace of iron and glass in 1853. Dublin and Munich mounted glittering exhibition halls the same year. Each borrowed the same logic: a repeating module, mass-produced components, glass standardized to a single pane, even when the details differed. The template outran the exhibitions too. At Kew, the Palm House had already shown that iron ribs and curved glass could enclose a tropical world. Now that principle spread to conservatories, arcades, and market halls across Europe. Above all, it found its natural home in the railway. The great train sheds St. Pancras, Paddington, and their descendants were crystal palaces in everything but name. Vast prefabricated vaults of iron and glass, their parts forged in factories and bolted together over the tracks. What had looked in 1851 like a one-off spectacle, a freak of a building that shouldn't exist, was revealed as something far more durable, a method. The glass house was not a stunt performed once and forgotten. It was a repeatable system that any engineer with a foundry and a glassworks could reproduce, scale, and adapt to a new purpose. Paxton was knighted. His blotting paper sketch had become an industry. Yet the metals that made it possible were already living on borrowed time. Cast iron was brittle, wrought iron was costly, and a furnace in Sheffield was about to change what buildings could be made of. When steel finally arrived, the question was whether the palace's idea would survive it. In 1856, 5 years after the Crystal Palace opened, Henry Bessemer unveiled his converter, a way to blow air through molten iron and produce cheap steel in bulk. Steel was everything the palace's metals were not. Strong in tension and compression alike. Tough where cast iron was brittle. Affordable where wrought iron was dear. Within a generation, it would carry loads no Victorian girder could dream of, and rise into the first true skyscrapers. But steel did not invent the modern building. It inherited it. The deepest lesson of Hyde Park was never about a particular metal. It was about a method. Design a structure as a set of standardized, factory-made components, test them before they ship, and assemble them on site at speed. That idea was indifferent to the material. Swap brittle iron for ductile steel, and the system only grew more powerful. The curtain wall of glass hung on a steel frame. The signature of every 20th century tower is the Crystal Palace's grid, stood on end and clad in its descendants' glass. The original did not survive to see it. On the night of the 30th of November 1936, fire broke out in the rebuilt palace at Sydenham. The iron frame that had made it fireproof against collapse could not save the timber and glass within. Within hours, the glow was visible for 30 miles, and by morning the great transept was a skeleton of twisted metal. The palace was gone. Its true legacy could not burn. Modular prefabrication, the notion that a building is not sculpted in place but manufactured elsewhere and put together like a machine, outlived the structure entirely. It became the grammar of the modern skyline. The repeated bay, the interchangeable panel, the crane lifting identical parts into a rising frame. Every glass tower that has gone up since speaks it fluently, whether its builders know the debt or not. That is the real monument in Hyde Park. Not the glittering hall itself, but the way it was made. Before mass-produced steel, before the skyscraper, a head gardener and 2,000 workers proved a single revolutionary idea. They assembled a palace from interchangeable parts.